Alright, our goal with these last three examples of conservation of energy is just to kind of look at our equations again and conceptualize and kind of put things into the right place and know when to use each different equation. So you'll remember we talked about in class we had three different equations. Two were basically definitions of work, that work equals the force times the displacement. One was that work is equal to the change in kinetic energy, right? And these two are always true, right? You don't have to worry about conservative forces and non-conservative forces and those types of things. The only thing really is that you need to make sure that the force and the displacement are in the same direction, right? The same component. Okay, and then the other equation that we had was that the work, non-conservative, is going to be equal to the change in kinetic energy plus the change in the gravitational potential energy. Okay, so we'll go ahead and look at each of these. Alright, so let's go ahead. The first example here, you've probably read through it already. The mass of the space probe is 474 kilograms. Initial velocity is 275 meters per second. It gives me a force, tells me a displacement for it, and asks for the final speed. Alright, well, I could obviously do this using kinematics, right? I could take the force equals ma, I could find the acceleration. Once I have the acceleration, I can plug that into a kinematics equation with my initial velocity and with the displacement, and I could definitely find a final speed using kinematics and Newton's laws. But let's see if we can do it with our new knowledge of work and energy and those types of things. We know that work is related to the force and the displacement, right? That's the first equation there. The force is to the direction of the right, and the motion is also in that direction. That's the direction of our displacement. So we can just start off with that we know that the force times the displacement is equal to the work. But if the work is equal to that, but work is also equal to the change in kinetic energy. Okay? And kinetic energy is going to relate the mass and the velocity, which we also have, right? So we look at it and we say, well, we have the force and the displacement, but then I need something to be able to get the work, and the work is also related to kinetic energy, so mass and velocity. So let's go ahead and put these numbers in. So for the force, we're going to have 0.056 newtons, right? The displacement is going to be 2.42 times 10 to the 9th. That will equal the change in kinetic energy, so 1/2 times the mass, 474, times the velocity squared, the final velocity, right, minus 1/2 m initial velocity squared, so 275 squared. Okay, so let's go ahead and take this side, and we'll take 0.56 times 2.42 times 10 to the 9th, so E9. Alright. Now, this right here needs to be added to the other side. And so I'm just going to go ahead and go plus 0.5 times 474 times 275 squared. Alright, so now I'm left with this number is equal to 1/2 474v squared. So let's divide by 0.5, divide by 474, and then, of course, square root the answer. And we get 804.6. So the velocity final, or the final speed, is 805 approximately. Alright? Not too bad, right? Just using the definitions, setting them equal to each other, we were able to get the question. Alright, let's look at another one. Okay, this one dealing with a skier going down a slope. Okay, so near the top, the speed is 3.6. Alright, she accelerates down the slope, right? Gravity's pulling her down the slope, though there's a kinetic frictional force of 71 newtons. So we know that there is a force of friction, which is 71 newtons. Ignoring air resistance, determine her speed when she's traveled 57 meters downhill. So this will be 57 meters, and we're determining her speed. Okay, so this should look somewhat like the last question, right? We've got a displacement, we're looking at some forces, right? We've got an initial speed, we're getting a final speed. So it should make sense that we can use the same ideas as last time. Okay, and there's actually a couple of different ways to do this, but let's go ahead and start with that one. Obviously, again, you could probably use the forces and find an acceleration and use kinematics. But let's go ahead and look at this in terms of the work. So again, work is equal to force times displacement. Work is also equal to change in kinetic energy, so 1/2 mv squared final minus 1/2 mv squared initial. Now this, it's not asking for the force of the work of any particular force, it's asking for the total work. So to get the total work, this force has to be the net force in the direction of the motion. And so that's this way. So what we're going to need to do is draw a force diagram for my skier. So there's my skier. We've got gravity pulling straight down. Right? We've got the normal force, which is pushing up this way. And then we've got friction, right, which we know is going that way. Okay, now the displacement is in this direction. Okay, and we know that when we have something on a slant, that we're going to tilt the axis, right? Which means that the displacement is actually along the x-axis there. So we need the sum of the forces in the x direction. And what are those? Well, we've got the x component of the force of gravity. So there's my angle. So I need the opposite side. So that'll be force of gravity times sine of 25. Right? And then I've got friction going to the left. So minus friction. Okay? So that's going to be the total sum of the forces. So let's go ahead and find out what that is. Force of gravity is 58 times 9.81 times sine of 25 minus the friction, which is 71. Okay, so let's find out what that is. 58 times 9.81 times sine of 25 and then minus the 71. So 169 newtons. Alright, so now we can go ahead and put that in here. The net force is 169 newtons. That's why he's accelerating down the hill, right? Because the force of gravity is stronger than the force of friction. Times the displacement, which is 57 meters, equals 1/2 times mass times the final velocity squared, final speed squared, which is what we're looking for, minus 1/2 times the mass times the initial speed, 3.6 squared. Okay, so let's go ahead and plug those numbers in. So 169 times 57, and then we're going to add the 0.5 times 58 times 3.6 squared. And then we will divide by the 1/2. We will divide by the 58. And then we will, of course, square root the answer, which gives us 18.6 per second. All right, there you go. Now, of course, there's other ways to do this. You could have done it using kinematics. You could have also said, well, work is the change in kinetic energy, right? And you could have found out how much work was being done individually by looking at the forces. And so you could have done it in other ways too. You could also have done this by saying the non-conservative forces, work due to the non-conservative forces, will be equal to the change in kinetic energy plus the change in the gravitational potential energy. Right? So what are the forces acting on it? Well, it's gravity and friction. Okay, so gravity is already considered. That's not a non-conservative force. So how much work is being done by non-conservative forces? Well, the only non-conservative force here is friction. And so you could have taken that negative 71, the negative 71 newtons of the friction and multiplied it by the displacement. And then you have the work that's being done by friction, right? The force times the displacement. And so you could have done that and then gone with the change in kinetic energy, the change in the height, the gravitational potential energy, and you could have done that as well. Okay, so there's lots and lots of ways to do these problems. This one right here that we did is probably the easiest way to do this particular problem. Alright, let's go ahead and look at one more. Okay, this will be our last one. Okay, this one is a gymnast on a trampoline, jumping on the trampoline. Alright, so when he leaves the trampoline, he has an initial height, so right here, of 1.2 meters. So they have defined this right here as being height equals 0, the ground. And that makes sense. You could set that equal to 0, and that means that even if he jumped all the way off the trampoline, the lowest that he could go would be 0. Nothing wrong with that. If you're assuming that he stays on the trampoline, there's not really anything wrong with calling this right here 0 either. Okay? So, whatever's fine. But in this case, it does tell us that the maximum height is 4.8 meters. Now you can see from the drawing that that's 4.8 meters from the ground. Okay, so that further shows that they are using the ground as being their h equals 0. Okay, now it gives us the it's now asking for the initial speed of the gymnast. Okay, so let's go ahead. We know that in this case we're having a change. We're starting down here, so we've got an initial point and a final point. So this is probably going to be due to work of the non-conservative forces equals the change in kinetic energy plus the change in gravitational potential energy. Okay, so when he's jumping on the trampoline, let's say that the initial height is 1.2. Let's say that his initial position is right as he's leaving the trampoline, right? So that's the initial speed that it's looking for. Not when he's down at the bottom of the bounce, because that's obviously 0. What it's asking for is how fast is he going as he leaves the trampoline. Okay, so that's going to be the initial velocity that we look for, initial height here. Okay, when he gets to the top, we know that his velocity is 0, right? Because he goes up to the top, slows down, slows down, slows down, slows down, and stop, and then comes back down. Okay, I just realized that I was demonstrating things with my hands, which you probably cannot see right now. So anyway, he goes up, 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 slows down, and starts coming back down, going faster and faster and faster. So the only force once he's in the air, of course, is gravity, which means there are no non-conservative forces, therefore there's no non-conservative work. Okay, remember, non-conservative work will only be done by contact forces, friction, tensions, other things, which once he's in the air, there aren't any of those. Okay, now the initial kinetic energy is what we're looking for, right? The final is going to be up at the top, so we've got 1/2 mv final squared. Of course, the final velocity is 0, so that's going to go away, minus 1/2 mv initial squared. That initial velocity is what we'll be looking for, okay, plus gravitational potential energy, so mgh final minus mgh initial. Alright, now unfortunately I already got the answer here, but let's go ahead and finish solving for it. So 0 equals negative 1/2. Now again, all the terms have mass. You've got 0 over here, so it's going to be okay to divide by mass. So all the masses are going to cancel out. You divide this side by mass, you divide this side by mass. Don't you dare forget to divide this side by mass, because if not 0, it's not going to cancel out. Now in this case it is, so that's going to go away. So we'll have negative 1/2 initial velocity squared plus gravity, 9.81, times the final height, which is 4.8, minus 9.81 times the initial height, 1.2. So let's go ahead, we'll plug that into our calculator. So let's go ahead and take these two and move them to the other side. So negative 9.81 times 4.8, because it's going to subtract when it goes to the other side, plus 9.81 times 1.2, because this is going to add when it goes to the other side. Okay, so I've now moved them both over. We can now divide by negative 1/2, and then take the square root. And thank heavens we get the right answer, which is the one that was already on there, 8.4 meters per second. Alright, so hopefully that's another example showing you the conservation of energy. Hopefully that helps you out a little bit and makes a little bit of sense. Alright, good luck with future problems in this.